Hi everyone, how are you doing? Welcome to this video series here on the channel. From now on, I'll dedicate some time to bring lessons about digital systems. Many students struggle with this subject, whether in college, technical courses in electronics, or even electrical engineering students. So if you're a computer science student or electronics student, and if you're having trouble with this kind of content, these videos were made for you. In this video, we are going to start by exploring logic gates, that is, how they operate on logic values. Okay, first of all, what are the logic gates? Before defining them in words, I want you to see them visually. What you're looking at here are logic gates. These small shapes represent the fundamental building blocks of digital circuits. So whenever you look at a schematic or a digital circuit design, you'll see these symbols. They are logic gates. Well, now that you already know what logic gates are visually, let's move on to the definition. A logic gate is the basic building block of a digital system. It allows us to implement Boolean logic and design digital circuits. All right, guys, at first, what is Boolean logic? Boolean logic can be defined as a logical system based on two possible states, 0 and 1. 0 can be defined as logic level low and 1 as logic level high. All right, guys, here's an important point. Although you use binary numbers to represent bit states, it's essential to understand that 0 and 1 are not numerical values. In this case, I mean in Boolean logic, 0 and 1 represent logical values. So there's a difference between logical values and numerical values. For our study of digital systems, it's extremely important that you understand that logical values are not numerical values because numerical values are handled in mathematics through arithmetic operations. Logical values, on the other hand, are used in Boolean algebra through logical operations, and that's what we're going to explore in this video. Therefore, it's extremely important not to confuse logical values with numerical values. This means that 0 and 1 can also correspond to false and true, and to other things that uses two possible states, like to open and close, yes and no, on and off, and many others. In digital circuit, 0 may indicate no voltage, no electric current, no electrical pulse, or similar negative states. A simple way that we can visualize this would be with a lamp. Thinking of logic 0 as the lamp being off. No voltage, no current, no pulse. Anyway, logic 1 would be the lamp being on, meaning voltage is present, current is flowing, anyway. So a logic gate is essentially a two-state circuit. Its output can be low or high, that is 0 or 1, depending on its inputs. Now, let's take a look at the basic logic gates, and they are NOT gate, AND gate, OR gate, and XOR gate. The NOT gate performs inversion. It takes one input and gives the opposite output. The AND gate gives output 1 only when both inputs are 1. The XOR gate gives output 1 if at least one of its inputs is 1. And finally, the XOR gate, also known as exclusive OR. It gives output 1 only when both inputs are different. These are the fundamental building blocks of digital system. We'll look at each of them in more detail with truth tables and examples. The first logic gate is the inverter, also known as the NOT gate. The NOT gate performs an operation called inversion or complementation. This means the inverter changes one logic level to its opposite. In terms of bits, it turns a 0 into a 1 and a 1 into a 0. Now, since the NOT gate has only one input, there are just two possible logic values it can handle, 0 or 1, as shown in this truth table. As you can see, when input is 0, output is 1. And when input is 1, the output is 0. You don't need to worry about truth table right now. We'll cover that in another video. What really matters here is understanding how logic gates operate on logic values. That's the main focus of this video. So the next gate is the AND gate. The AND gate performs an operation called Boolean multiplication. Remember, Boolean multiplication is actually a logical multiplication. It's not an arithmetic multiplication, okay? As mentioned earlier, the logic of the AND gate is this. The output will be 1 only when all its inputs are at bit 1. Let's bring in the truth table for the AND gate and test all the possible inputs combination. As we can see, when input is 0 and 0, results in an output 0. The combination 0 and 1 results in an output 0. When combination is 1 and 0, results in output 0. The output will be 1 only when both inputs are at bit 1. Okay, but why does that happen? Why does the AND gate gives output 1 only when all its inputs are 1? How can we understand this kind of logic operation? A simple way to better understand this logic operation is by using an electric circuit with a light bulb. We have a power source here and two switches connected in series. Now imagine that these switches represent the inputs of the AND gate. The light bulb represents the output. Okay, that is, input A is represented by the switch A. Input B is represented by the switch B. And the output is represented by the light bulb. All right, let's assume the following. If a switch is off, it represents a logic 0. If it is on, it represents a logic 1. Now look at the first input combination, 0 and 0. That is, input A equals 0, input B equals 0. It's like saying switch A is off, okay, and switch B is also off. When the electric current comes from the power source, will the light bulb turn on? Let's find out. As we can see, the light bulb remains off because both switches are off. Therefore, its output is 0 because the light bulb remains off. And this demonstrates that the input combination 0 and 0 results in an output 0. Okay? It's very easy, isn't it? Now, look at the second input combination, 0 and 1. That is, input A equals 0, input B equals 1. That is, switch A is off and switch B is on. Okay? At bit 1, like the B input. Okay? So when the current comes from the power source, will the light bulb turn on? No, because although switch B is on, switch A remains off. Therefore, the output is 0 because the light bulb didn't turn on. So the input combination 0 and 1 results in an output 0. Let's try the third combination, 1 and 0. Input A equals 1, input B equals 0. So switch A is on and switch B is off. I ask you, will the light bulb turn on? No, because switch B is off, so no current flows through the circuit to reach the bulb. Therefore, the output is 0. Okay? So, input combination 1 and 0 results in an output 0. Okay? Finally, let's try the last input combination. Input A equals 1, input B equals 1. So if we compare this input combination to a circuit, switch A is on and switch B is also on. All right, when the currents come from the power source, will the light bulb turn on? What do you think? It will, because this time the current will have a clear path to reach the bulb and turn it on. Therefore, the output is 1. This demonstrates that the combination 1 and 1 results in an output 1. Okay, guys, it's very easy, isn't it? This way, we can compare the operation of the AND gate to a circuit with switches connected in series, that is, one after the other, where the light bulb will turn on only when switch A and switch B are both at bit 1. That is, the output will be 1 only when input A and input B are both at bit 1. And that's why it's called the AND gate. Okay? In other words, no matter how many inputs the AND gate has, for its output to be at bit 1, all inputs must be at bit 1. And this becomes clear when you look at the circuit. The next logic gate is the OR gate. The OR gate performs an operation called Boolean addition. As mentioned earlier, the operation of the OR gate is as follows. The output will be 1 if at least one of its inputs is at bit 1. Okay, let's bring in the truth table for the OR gate and test all the possible inputs combination. Okay, according to its truth table, the output will be 1 only when if at least one of its inputs is at bit 1. All right, how can we understand this kind of logic operation? Just like with the AND gate, a simple way to better understand this logic operation is to use an electric circuit with a lamp. We have a power source here, but unlike of the AND gate, where the switches were connected in series, now the switches are connected in parallel. The electric current will have two separate paths, one through the switch A and another through the switch B. And we can compare these switches to the inputs of the OR gate, okay? Let's use the same idea. If a switch is off, it represents logic 0. If it is on, it represents logic 1. Okay? Looking at the first input combination, 0 or 0. Okay? Input A equals 0, input B equals 0. That's like saying switch A is off and switch B is also off. When the current comes from the power source, will the light bulb turn on? Okay, light bulb remains off because both switches are off. Okay, this demonstrates that the input combination 0 or 0 results in an output 0. Okay, guys, very easy. Now, look at the second input combination, 0 or 1. That is, input A equals 0, input B equals 1. When you look at the circuit, switch A is off and switch B is on. Okay? When the current comes from the power source, will the light bulb turn on? Let's find out. Okay, yes, because although switch A is off, switch B is on. So the current will have a clear path through the switch B to reach the bulb and turn it on. Okay? And this demonstrates that the combination 0 or 1 results in an output 1. Okay, guys, let's try the third input combination, 1 or 0. Okay, input A equals 1, input B equals 0. That's like saying switch A is on and switch B is off. So I ask you again, when the current comes from the power source, will the light bulb turn on? Let's find out. Yes, because this time switch B is off, but switch A is on. So the current will have a clear path to the switch B to reach the bulb and turn it on. Okay, therefore the output is 1. This demonstrates that the combination 1 or 0 results in output 1. Finally, the last input combination. Input A equals 1, input B equals 1. That is, switch A is on and switch B is also on. All right, what do you think? Will the light bulb turn on? Let's find out. It will because both switches are connected. This demonstrates that the combination 1 or 1 results in an output 1. In this way, we can compare the operation of the OR gate to a circuit with switches connected in parallel, where the light bulb will turn on if at least one of its switches is at bit 1. That is, the output of the OR gate will be 1 if at least one of its inputs is at bit 1. Okay? Alright guys, finally, the XOR gate, also known the exclusive OR. The XOR gate performs what we call an exclusive addition between two bits. In other words, the output will be 1 only when both inputs are different. Okay? The symbol of the XOR operation, it's a plus inside a circle, and it represents this exclusive addition. All right, let's bring in the truth table for the XOR gate. As you can see, the output will be 1 only when both inputs are different. If you look at the first input combination, results in output 0 because they are equals from each other. And the same thing happens to the last input combination. The output is 0 because both inputs are equals. Output will be 1 only when both inputs are different. How can we understand this kind of logic operation? Why does the XOR gate gives output 1 only when both inputs are different? The operation of the XOR gate can be compared to a combination of circuits. However, visualizing the XOR gate as combinational circuit can be somewhat tiring. To make our understanding for the XOR gate operation even easier, let's replace the names of input variables with city names. Okay? New York and Los Angeles. The output will be travel to New York or travel to Los Angeles. Remember, the trip will only be possible to one of the cities. That is, it won't be possible to travel both cities at the same time. Now, let's define the following. 0 means not traveling. 1 means traveling, okay? Checking the first input combination, not traveling to New York and not traveling to Los Angeles. I ask you, will the trip happen? No. That's why the output is 0. So the trip didn't happen. Let's try the second input combination. That is, not traveling to New York, but traveling to Los Angeles. Will the trip happen? Yes. In this case, the trip happens to only one of the cities. Therefore, the XOR gate condition is satisfied. So the output is 1. Okay? It's very easy. Now, let's check third input combination. Traveling to New York, but not traveling to Los Angeles. This time, will the trip happen? Yes, because here again, only one city is chosen for the trip. XOR gate rules remains true. Therefore, the output is 1. Okay, look at that now. Last input combination. 1 XOR 1. This means traveling to New York and traveling to Los Angeles at the same time. Is it possible? No. Now, there are 2 trips happening at once, which breaks the exclusive condition of the XOR gate. Since the XOR gate operation requires only one true input, in this case, the rule is not fulfilled. Results in an output 0. Okay? Okay, and that is for today's lesson. We've explored the 4 basic logic gates, NOT, AND, OR, and XOR, and we learned how each one operates using practical examples. Understanding how logic gates work is the foundation of digital systems. From simple circuits to complex computer architectures, everything starts here. In the next videos, we'll dive deeper into truth tables, Boolean expressions, and logic simplification techniques, so you can take your knowledge to the next level. Don't forget to subscribe on the channel and turn on the notifications so you don't miss the upcoming lessons. Thanks for watching. I see you in the next video.